Hi everyone! Today, we are diving into a crucial topic for composite analysis, how to get laminate stiffness matrices, often called ABD matrices, using APDL ANSYS. Understanding these matrices is fundamental for predicting how composite structures will behave under various loads. The A, B, and D matrices describe the extensional, coupling, and bending stiffness of a laminate, respectively. They link the resultant forces and moments to the midplane strains and curvatures. While APDL ANSYS handles these calculations internally when you define a layered shell section, there isn't a single direct command to simply output the A, B, and D matrices. However, we can use APDL's powerful scripting capabilities to calculate them step by step, giving us full control and insight into the lamination theory. First, we need to define our basic material properties for an orthotropic ply. This involves setting parameters for Young's moduli, E1, E2, shear modulus, G12, and Poisson's ratio, NU12. For example, we might use commands like set, E1_PLY, 130E9 and set, E2_PLY, 9E9 to store these values. Next, we calculate the reduced stiffness matrix, often called the Q matrix, for a single ply in its principal material directions. This Q matrix relates in-plane stresses to in-plane strains for an individual ply. With these basic properties, we then need to define the geometry of our laminate, the thickness of each ply and its orientation angle relative to the laminate's global coordinate system. We can store these in APDL arrays or parameters for easy access. Once we have our ply properties and orientations, we can start the core calculation. We initialize our A, B, and D matrices as zero arrays. We then loop through each individual ply in our laminate. For each ply, the critical step is to calculate its transformed reduced stiffness matrix, known as Q-bar. This Q-bar matrix accounts for the ply's specific orientation angle within the laminate. The calculation of Q-bar involves trigonometric functions of the ply angle to transform the principal material Q matrix into the laminate's global coordinate system. This is where APDL's mathematical functions like cos and sin become very useful. After determining each ply's Q-bar matrix, we calculate the z-coordinates for the top and bottom surfaces of that ply, measured from the laminate's midplane. It's important to define the midplane correctly as our reference. Finally, we sum up the contributions from each ply to form the A, B, and D matrices. The A matrix components are calculated by summing Q_bar_ij, H_K, H_K1, for each ply, where H_K and H_K1 are the z-coordinates of the top and bottom surfaces of the current ply. The B matrix components involve 1/2 Q_bar_ij, H_K2, H_K1, representing the coupling between in-plane and bending responses. The D matrix components are found using 1/3 Q_bar_ij, H_K3, H_K1, which describes the bending stiffness. We use APDL's VADD or direct parameter assignments within our loop to accumulate these values. After the loop completes for all plies, our A, B, and D matrices will contain the full laminate stiffness properties. We can then use write or MSG commands to print these calculated matrices to the output window, allowing us to inspect their values directly. This approach gives you a transparent way to understand and verify the laminate stiffness properties that APDL uses internally for shell elements. Thank you so much for watching this video. I hope this explanation helps you understand how to obtain laminate stiffness matrices in APDL ANSYS. If you found this helpful, please give it a thumbs up and consider subscribing to the channel for more engineering tutorials and tips. Your support helps us create more valuable content like this.